Hi everyone, I'm Binbin Gu. I'm very glad to present our work on ICBC 2023. This paper is done by Abhishek, Yinan, Junchen, Faisal, and me. All of us are from the Edge Lab of University of California, Irvine. Our work is about machine learning on chain, the case and taxonomy of machine learning on blockchain. In the last decade, there was a lot of interest in applying machine learning to problems in various domains. This is because of the powerful nature of machine learning insights from data and applying these insights for future tasks. While blockchain has the ability to manage data in a decentralized, secure, transparent, and accountable manner, doing machine learning on blockchain has immense benefits such as immutability, accountability, and transparency of the machine learning models. The combination of machine learning and blockchain has the potential to create powerful applications that can transform many industries. In supply chain management space, machine learning can be used to track products as they move through the supply chain, providing greater transparency and accountability. By analyzing data from various sources, such as shipping records, machine learning models can provide insights into the status of the products and help to identify potential bottlenecks or issues in supply chain. Other applications include decentralized autonomous organizations, fraud detection, smart contract analysis, and so on. One natural way to do machine learning on blockchain is to implement the machine learning algorithm in smart contracts. However, smart contracts are limited. First, the cost of complex programming is high. Training machine learning models in smart contracts requires paying high mandatory fees. These fees are higher for more complex computations. Second, the current blockchain technology still struggles with scalability. As the number of transactions on a blockchain increases, the speed and efficiency of smart contracts may be affected. In this work, our goal is to introduce a taxonomy of machine learning on chain to help figure out the trade-offs among different solutions. The first kind of existing work that is most relevant to machine learning on chain utilizes machine learning for solving blockchain-related tasks without discussing the integrity and or costs of the executing machine learning programs. These tasks include data and model sharing on blockchain and achieving decentralized intelligence with machine learning and blockchain. Another kind of work focuses on proposing specific blockchain systems with relaxed, secure guarantees to enable computation-intensive and storage-intensive tasks to be performed on-chain. While some works summarize the general off-chain approaches, they do not target machine learning on-chain and lack a quantitative analysis with experiments. While there are a lot of existing surveys talking about machine learning and the blockchain, the key insight of these works is that machine learning and the blockchain can benefit from each other. However, none of them investigate or evaluate the detailed solutions and the trade-offs for implementing machine learning tasks on blockchain. This picture shows the taxonomy we proposed in this work. The taxonomy groups solutions based on the following. Is the task performed on-chain or off-chain? And is it a model training task or an inference task? In the following, we are going to describe these methods briefly. Machine learning models can be trained and utilized to do inference on blockchain by smart contracts. There's a fundamental challenge for the on-chain machine learning solutions due to the bound on how much computation and data can process on-chain within one block. To overcome this challenge, models can be trained incrementally. Specifically, the dataset is split into smaller datasets so that each part can be performed in a separate block. After all the parts are processed, the process terminates. However, if machine learning algorithm cannot be trained incrementally, then there's no way to do such a task totally on-chain without any performance compromise. Off-chain machine learning training and inference can be categorized into single-party-based and multiple-party-based approaches. Single-party-based solutions are ones that can generate a proof of the integrity of the outcome. This can be based on trusted hardware or software level verification techniques. Multiple party-based solutions are ones that rely on performing the computation on a number of nodes to ensure that malicious subset does not threaten the integrity of the computation. Enclave-based computation relies on trusted execution environments to run programs while preserving the integrity of the computation. This is done by using hardware-level isolation and memory encryption. This figure shows the basic framework of the enclave-based method. Enclave-based methods follow a three-step approach. First, the off-channels initialize a secure enclave. Second, the program to be processed in the secure enclave is loaded. Third, the off-channel can start processing requests using the program in the secure enclave. The core idea of VC-based methods is to enable a client to verify that an untested off-channel has performed computation correctly. The VC-based method involves using cryptographic techniques to enable the verifier to verify the correctness of the computation without actually performing the computation. In the group of voting-based methods, a number of off-channels are asked to train a model with the same dataset and configuration. Then, the trained models from the off-channels are collected. If there are enough received identical models, then the model is approved. The key idea of incentive-based method is to encourage the off-chain participants to publish correct results to maximize their own profits. In such a setting, multiple off-chain nodes compete to submit their answers to a smart contract. The first to submit their answers wins a reward. To check whether the submitted answer is correct, other off-chain nodes can challenge it until no challenger nodes challenge the current results. Distributed Byzantine machine learning refers to the machine learning algorithms that are implemented in a distributed computing environment and are resilient to Byzantine failures. This figure illustrates a simple workflow of distributed Byzantine machine learning. The whole data set is divided into n data samples, where n is the number of nodes or machines. A single trusted parameter server is in charge of updating the parameter vector, while the potentially malicious node performs the actual update estimation based on the local data it has. Each node computes an estimate of the update to apply, and the parameter server aggregates their results to finally update the parameter vector. The table here summarizes the comparison between the 5 off-chain solutions in terms of trust assumption, result integrity, and data privacy. The VC-based method does not need any trusted assumption or quite weak assumptions. The others all have non-trivial trust assumptions. The result integrity of the incentive-based and the DBML are partially guaranteed even when their trust assumptions hold. And the enclave-based, VC-based, and DBML can protect the data privacy. We now show the experimental evaluation of the different machine learning on-chain approaches as we discussed. Our experiments are performed on Ethereum Goerli testnet. We implement the on-chain components using Solidity smart contracts and implement off-chain components using Python and C++. We use Zocrates to implement a zk-SNARK-based approach. We compare on-chain machine learning baseline and 5 off-chain methods. Each off-chain method represents one of the groups we presented. SGX-based belongs to the enclave-based method. zk-SNARK-based belongs to the VC-based. We implemented the incentive-based method introduced by TrueBit and a baseline voting-based method. Finally, we implemented a parameter server-based method, which is a kind of distributed Byzantine machine learning. We implemented 3 machine learning models: logistic regression, KNN, and neural network. We evaluate the cost of training and inference for on-chain solutions of logistic regression, KNN, and neural network models. Figure 9 illustrates the gas fee for 3 machine learning models in terms of training. The cost of on-chain training increases almost linear with the size of the training samples and the size of the features. The cost reaches $10,000 when training a neural network on 1,000 samples. This indicates the infeasibility of training machine learning models totally on-chain. Although off-chain methods do computation with off-chain machines, they need to send the computation results to smart contracts for verification. This is where the on-chain verification costs come in for the 5 off-chain methods. As can be seen from figure 11 and 12, the on-chain verification cost is a constant with respect to the number of data samples for training tasks. This is because increasing the number of training data will not change the size of the model. The zk-SNARK-based and SGX-based method have quite low on-chain verification cost compared with the other 3. Table 3 shows on-chain verification cost for inference tasks with 3 machine learning models. While the incentive and voting-based methods need to store the multiple predictions, they take relatively high cost compared to the SGX and the zk-SNARK-based methods. We measured the off-chain running time of the 5 off-chain solutions for the training tasks. The results are shown in table 4 and 5. All the methods have quite low running time except for the zk-SNARK-based methods. The running time of the zk-SNARK-based method becomes significantly long when the number of training samples is large. In this work, we propose a taxonomy of machine learning on-chain approaches. We use this taxonomy to drill down in each category and analysis of various machine learning on-chain solutions and their design trade-offs. We conduct an experimental evaluation to study and compare machine learning on-chain solutions. The evaluation is performed on Ethereum with 3 popular machine learning models. In addition to providing a taxonomy of prior work related to machine learning on-chain, we foresee new machine learning on-chain approaches that have not been explored in prior literature or industry systems, and include them in the taxonomy and evaluation. If you have any questions about this work, I will be happy to answer them. Thanks.